Okay, so for this first lesson, I want to review some things about functions and usual functions in that we are using in mathematics, some basic facts about them. So the notion of function, also called application or map or transformation. Okay, so but the usual name is function. It's given when we have three objects, two sets, A and B. A is called the domain or the domain of definition of the function. B is called the codomain. And also called the set where the function takes values. And a procedure, a method which associates for every x element x in A, one single element y in B. Y, it's also denoted by f of x and is called the value of the function f at the point x, or the value at x, or the image of x through the function f. In mathematics, the usual functions are defined on sets of numbers, and they are given through an explicit formula. But we can imagine a function like a picture like this. This is the set A, the domain. This is the set B, the codomain. Here we have some elements. Here we have other elements. Okay. And the procedure which associates to every element x in A one single element in B is usually pictured by arrows, for example. So if the image of this element, it is this one, I show this through an arrow, yes. Here and here. Tell me, this picture, does it represent a function? So does it satisfy what's written here? So the main information here is given by the words every, for every, and one single element. Are these conditions satisfied on this picture?
No.
No.
What's the problem?
Because 2x has one y element, the same y element.
I see, but I think this is not a contradiction with the definition. Let's denote this element. Let's call this element A, this one B, and this one C. Let's call this one T, S, U, and V. So on this picture, f of A equals T, and so on. So you said that what's wrong here, it is that the image of B, f of B equals C, and f of C equals the same element C. So you say this is the problem, yes? Well, in my opinion, this is not a problem. I mean, this not contradicts the definition, because if we look here, do we have this function, does it satisfy that for every element we give one single element in B? I think yes.
Yes.
The definition, it's not contradicted if for two different elements in A, they have the same image in B. This is possible. So this is a function. Yes, it doesn't satisfy. For example, the following picture, it's obvious not a function. For example, from that moment, this is not a function because for this element, we associated two elements in B, and we need to associate one single element. So yes, this is not a function. Also, another picture which is not a function, it is the following. For example, this is not a function. Here we contradict what word from the definition? For every. Not for every element in A, we associated something in B. For this element, we did not associate something. So in order to get a function, also this one must have an image in B. As long as it doesn't, this is not a function. So this is not a function, this is not a function, but this is a function, yes? Okay. I don't want to go further with general questions about functions. We shall have such a lesson later on, but now I want to start with some basic functions in mathematics, mainly in algebra. Yes, okay. So, as I said, we discussed about our functions in mathematics are usually defined on sets of numbers. The usual sets of numbers that we are working with is the set of natural numbers, then larger is the set of integers, then the set of rational numbers, and finally the set of real numbers. So everything will happen here on the set of real numbers. So our sets will have the domain of definition in the set of real numbers or subsets of the set of real numbers. Okay, now the first function is called the affine function. Some you also see it as linear function, but linear is not a very appropriate name in this case. So the affine function is defined on the set of real numbers, taking value in the same set. So this is the domain. In general, if we write like this, that means the function f has the domain A and the codomain B. This is the domain and this is the codomain, yes? Okay, so the function is given by the formula f of x equals ax plus b. Here a is different from 0. A and b are constants, and a is not 0. For example, f of x equals 5 minus 3x. Tell me here, who is a, who is b?
A is minus 3 and b is 5.
Okay, very well. So what do we mean by study a function? There are several things which are important. For example, the first is to study the equation f of x equals 0. Here I want to make a comment. Do not confuse functions and equations. If you have a function is a quantity which depends on a variable x. For example, 5 minus 3x. It's a quantity which depends on the variable x. X is called a variable. Okay. If we equalize this function with another function, for example, with a constant function 0, then we have an equation. The equations have solutions. So to talk about solutions, we need to have an equation or an inequality. We see later this. Now, this is the simplest equation in mathematics, the so-called equation of the first degree. And everybody knows that the solution here is minus b over a. Here we are using that a is different from 0. Otherwise, this is meaningless. Okay, that's all. So the equation of the first degree is the simplest in mathematics. There is nothing to it. The second fact we want to know about a function in general is the sign. What that means? Well, the sign means the following. Look to this function, for example, here. If we compute f at 1, we shall get 2. So the image of 1 is 2. If we compute f of 3, for example, we shall get minus 4. So what we see, some values of the functions or the function are positive, some other values are negative. To know the sign of the function means to know for what x is it positive and for what x is it negative. This is for simple functions like the affine function. This is given usually by a so-called sign rule. So the sign rule for the affine function is given by for the following table. Sine rules are usually given through tables of sine. So here x, the logic of this table is like this. X takes values from minus infinite to infinite. That means it takes the values of all the real numbers, yes. And below we have the values of the function ax plus b. This is our function, yes. Well, the table of sine says this: when x equals minus b over a, so this value, then f of x will be 0 because minus b over a was found by putting the condition f of x equals 0. And now the rule of sine is the following. Here, on the first interval, our function takes values opposite to the sine of a. Let's say the sine of minus a. And here, the sine of a. A means this one, the coefficient of x, yes? Okay, we shall make applications, we shall see application of this sine rule. For example, if we want to solve inequalities, for example, 1 minus 2x over x plus 3 greater or equal than 0. This is an inequality. Attention, when we have inequalities, it is totally forbidden to eliminate the denominator. When we have an equation, yes, we can eliminate the denominator, but when we have inequalities, this is not possible. So when you have an inequality, do not eliminate the denominator. But how to do? It's very simple. We want to know the sign of this ratio. The sign of a ratio depends on the sign of the numerator. This is the numerator. And it depends also on the sign of the numerator. So when I see such an inequality, I know that I have to complete the following table of sign. What that means? It means the following. The numerator and the denominator are both affine functions, so we know their sign. We can do it, we shall do it. And then as a consequence, I shall get the sign of the ratio. So first I need the sign of 1 minus 2x. I know the procedure, it's above, so first I need to compute, to solve this equation, which gives us x equals 1 over 2. So I put here 1 over 2. When x equals 1 over 2, 1 minus 2x is 0. And now following this rule written here, yes, here on the first interval, we shall have the sign of minus a. In our case, a equals minus 2. So here it's plus. And here is the sign of minus 2, which is negative. Okay? Now, similarly for the second function, for the denominator, here the solution of the equation is minus 3. Minus 3 is here. This is 0. And here now a is 1. So here we have negative, and here we have positive. And now, what's the sign of the ratio? Well, when x equals, first of all, what's happened here and here? When x equals minus 3, the denominator is 0. When the denominator is 0, the ratio is meaningless. So we put a vertical line like this. When x equals 1 over 2, the numerator is 0. So the ratio is 0. And now plus over minus, it's minus, then plus, then minus. Okay, we wanted those x for which the ratio is positive. This is our inequality. Where is it positive? It is positive here, which means the solution of our inequality is x belongs to the interval minus 3, 1 over 2. At -3, it is open because at -3 it is meaningless. At 1/t is closed because here we have also the possibility to be equal to 0, and at 1/2 it is 0. Okay, I know these are simple, very simple things. I am sure that you already met this kind of, but I want also to fix some notations and okay, names of different. Okay, so this is we continue with the affine function. The last thing we want to know about the affine function is the graph. The graph of a function. As you know, every function can be represented in the plane. In general, a point on the graph has the coordinates x. So the x coordinates is arbitrary x in the domain, and the y coordinates, it's the value of f at that point. Yes. Now, for the affine function, the graph is very simple. It's a line. So the graph of the affine function, it's the simplest as possible. It's a line. To represent a line, you need 2 points. What points? Doesn't matter what points. So, for example, if I take the previous example, f of x equals, it was 5 minus 3x. We can give here to x different value. For if I give to x equals 1, then we compute f of 1, that is 2. So we get a point A of coordinates 1, 2. 1, 2. So here is the point A. And now another value. For instance, if we put x equals 0, we get f of 0 equals 5. So we get a point B of coordinates 0, 5. Here is the point B of coordinates 0, 5. And now the graph will be the straight line which passed through these 2 points. Something like this. Yes. So the points doesn't matter what our particular points are. If I take out the value for x here, I get other points, but the straight line will be the same. Okay. This is the affine function. I think it's very clear here. We have no problem. It's very simple, but these facts will be used again and again. Now let's move to our second function, the so-called quadratic function. Now tell me if you have any question about okay, now the second will be the quadratic function. Quadratic means of the second degree. Okay. Now the quadratic function, it's a function defined on the set of real numbers, and the formula is given by ax squared plus bx plus c. A, b, c are numbers, and a is not 0, of course. What questions do we have? The same questions. So this is the second function. We discussed about the equation f of x equals 0. So we put the same questions as before. The equation, the sign, and the graph. Now, this is the famous quadratic equation, yes? How it starts. To study a quadratic equation, we always start in the same way. We compute the so-called discriminant, or del, which is denoted by the Greek letter delta, capital delta, which is b squared minus 4ac. Why do we compute this discriminant? Because according to its value, we have 3 cases. Case number 1 is if delta is negative. If delta is negative, our equation has no real solution. So because we work in the set of real numbers, we have no solutions at all. No real solutions. The study of functions, of basic functions, are on the set of real numbers. So we don't discuss about complex numbers. If some of you, I'm sure you already studied about complex numbers, we don't use them for the moment. Yes, we are talking about functions defined on sets of real numbers. Second, if the discriminant is 0, the equation has one real solution, which is given by the formula x equals minus b over 2a. And finally, if our discriminant is positive, then the equation has two real solutions, which are given by the very known formula minus b plus minus square root of delta over 2a. Okay, this is the basic information for the quadratic equation. Attention, it's a little bit different from the equation of from the affine equation, because all the affine equations had always one single solution. This is not the case for the quadratic equation, which, as you can see, there are three types of quadratic equations. Some of them that have no solutions, others have one solution, and others have two solutions. Now, there is also an additional fact here about the equation, the so-called, we can compute the sum and the product of the solutions, not necessarily by computing the solutions. We have some separate formulas for them. The sum of the solution, which is x1 plus x2, it's minus b over a, and the product, it's x1, x2, it's c over a. In some exercise, we prefer to work with the sum and with the product of the solutions because there are very simple formulas, instead to work with the solutions of the equation x1 and x2. Okay, this is the equation. We shall come back and we shall see some examples immediately. The second question was about the sign. Remember. Well, again, here we start by computing the discriminant. And according to it, we have three cases. The cases are, the first case is when delta is negative. Then the sign table of the quadratic function is the following. It is, it has always the sign of a. Yes. The second case is when delta is positive, delta is 0, sorry. In that case, the sign table is given by the following. When x equals minus b over 2a, this is the case, our case, you see it here. When x is this one, f of x is 0. And now the sign on the left is the sign of a, and here is the sign of a. And so it has also a constant sign, but now it takes also the value 0 if we compare with the first case. And the last one, if delta is positive, then the sign table is given by, now we shall use x1 and x2, where f of x is 0, according to the third case of the equation. Remember, when delta here, this is the case, and at this point, f of x takes the value 0, and now the sign here, you have the sign of a, here the sign of a, and here the sign of negative a. Okay, Now let's see some applications regarding these facts. Okay, I can clean.
Yeah. Just
Please, I didn't hear you.
Yes, you can clear.
Okay, so let's see some applications to see how we shall apply all these things. For example, let us solve the following inequality. Okay, a similar inequality as before, a ratio, but now the numerator and the denominator are quadratic functions. In order to find the sign of this ratio, I know that I have to complete the following table. The sign of the numerator, the sign of the denominator, and finally I shall get the sign of the ratio. X takes values from minus infinity to infinity. Now, first of all, we need to see the sign of x squared minus x plus 3. We know how the sign starts. We know the theory. We first compute delta, which is 1 minus 12, which is negative 11. So the conclusion is that we are in the first case with the sign, and there is written that in this case we have always the value, the sign of a. It's 1 in our case, so here it's plus in one row. Now the sign of 9 minus x squared, here we compute delta, which will be 36, it's positive. We are in the third case, so we need to compute the solutions of the equation of f of x equals 0. We compute by using the formula, we get plus and minus 3. So here is minus 3, here is 3, here is 0, here is 0. Now, according to the rule, on the first interval, we have the sign of a, which is minus 1. So here is minus 1. Then it's the sign of minus a, and then it's the sign of a. Consequently, the sign of our ratio, here it doesn't exist because the numerator is 0. Here we have negative, positive, negative. We want it to be positive, okay? So it is positive when x belongs to the interval minus 3, 3. And this is the answer for this. Again, I emphasize that when we have inequalities, we cannot eliminate the numerator. Yes, never, don't do that. Okay, now let's see now another example about the quadratic function. Tell me that if I can, okay, I shall, here you are an exercise. Consider the function f of x equals m x squared minus m minus 2x plus m plus 1. Now this is a quadratic function. The coefficients are depending on some parameter. M is also called a parameter. So here I shall write the coefficients. A, it's m. B, it's minus m minus 2. And C, it's m plus 1. So this time the coefficients actually depends on a parameter m, which is a real number. And now the questions are, the first question is the following. For what values of m, the equation f of x equals 0 has two real solutions? The second question, for what values of m, the equation f of x equals 0 has two negative solutions? And the last one, for what values of m, f of x is strictly greater than 0 for all real x. Now, I emphasize that the first two questions are about the equation f of x equals 0, while the last question is about the function. So we don't make a confusion between the function and the equation. Okay. So the first two questions are about the equation, and the last one is about the function. Okay. So now the solution. Now, the first question. The theory tells us when a quadratic equation has two real solutions. When does this happen? Who can tell me?
So we have two real solutions when discriminant is greater than 0.
Very well. So we must put the condition delta greater than 0. This is the solution, actually. Somehow we solved the exercise, theoretically at least. What we have to do now, there are some computations and get the result. But this is, yes, this is what the theory says. So we must apply the theory. Now, so we need to compute delta. And we need then to solve this inequality. This is an inequality, yes. But first, let's compute delta. So delta will be
m minus 2 at power 2 minus 4m
okay.
m plus 1.
Very well, let's compute exactly. Let's see the final result here.
Is not an m there at 8?
8m, of course.
8m.
Yes. So this is delta. Okay. Why did we compute delta? Because now we need to solve this inequality, which is minus 3m squared minus 8m plus 4 greater than 0. This is a quadratic inequality. How to solve it? Of course, we shall make a table for the sign of this quadratic function, minus 3m squared minus 8m plus 4, which is a quadratic function depending on the variable m, yes? We need to complete this table. Again, we shall use the sign of the quadratic function, which says first compute delta, 64 plus 48, which is 112, which is positive. So we are in the third case this time. Now we need to compute M1 and M2. Here we need to make some elementary computations. So we need to see 112, how it can be factorized. So 112 can be written as 2 at 4 times 7. So this is 8 plus and minus 4 square root of 7 over minus 6. And here we can simplify by minus 2, which will give us minus 4 plus and minus 2 square root of 7 over 3. So these are the solutions of the equation delta equals 0, actually. We need them in order to complete this table of sign. So we shall put here minus 4, minus 2. Please, it's good to make also the computations to see if it is okay to check everything. Okay, here is 0, here is 0. And now according to the rule, here it's negative, here it's positive, here it's negative. So our inequality was this one, as we can see here, delta is positive when m belongs to the interval. So it seems that the solution, the answer for the first question is m belongs to -4 minus 2 square root of 7 over 3 up to -2 plus 2 square root of 7 over 3, because this is where it is positive. Now, basically, this is the result. There is also here a small trick because, but this is how I want from you to apply the theory. But there is also a small trick here. Attention, when we discuss about this equation, f of x equals 0, where f of x is this one, we supposed that this is a quadratic equation, which is almost all the time the case. So that's why we apply the theory of the quadratic equation, because here is, but attention, this is not a quadratic equation when m equals 0. So everything we did here was okay, as long as the equation f of x equals 0 is a quadratic equation. And then we show, and consequently, we applied the theory of the quadratic equation. But when m equals 0, this is not a quadratic equation. Actually, when m equals 0, we have what? We have the equation 2x plus 1 equals 0. Because f of x when m equals 0 from here gives us 2x plus 1. Yes, when you put here m equals 0, this is 0. This is 2x. And so this equation is an equation of the first degree, which has one single solution minus 1 over 2. So when m equals 2, does our equation has two solutions? The answer is no, it has only one, because it's not a quadratic equation. And so m equals 0 is not good for us. But and you see here in this interval, there is the number 0. So we have to eliminate from here 0. Yes, because 0 is between them, and when m equals 0, our equation has not two solutions. But now it's okay. Okay, this is the right answer for the first question. But the first part is important, how we apply the theory. We see in the theory when the equation has two real solutions, we write what's there. So of course, these are very simple exercises. I'm sure that you know them. But what I'm trying to send, I try to send you the following message. Try to use all the time the theory. Solve problems by learning and by applying the theory. So your main objective is the following, where you have an exercise. How to apply the theory. Of course, that means that we already know the theory. Okay, now for the second question. Now we want the same equation to have two negative solutions. So we have a quadratic equation, this one. And now we want to have x1 and x2 be both negative. So you want two solutions which must be both negative. And now let's look to the theory and see when this happens. How can we use the theory to put conditions for this? Well, it's very clear. If we want to have two negative solutions, first of all, we need to have two solutions. So the first condition is delta must be positive, because if we don't have two real solutions, it's impossible to have two negative solutions. Okay, now we have two solutions. What conditions are needed in order to be both negative?
Okay, so we can use the sum and the product of the solutions?
How? More precisely. Very well.
Product need to be greater than 0.
Yes, very well.
And sum less than 0.
Okay. So these three conditions will solve our problem. I shall not solve the inequalities. This one was already solved. The other two, the product will be m plus 1 over m, need to be 0, and the sum is m minus 2 over m, must be negative. Solve both these inequalities. We already have an example in this respect. And then intersect the three sets. The set from here, the set from here, and the set from here. And that will be the, okay? And now the last question. Find those values for m for which the function f of x is strictly greater than 0. Attention, for every real x. Okay. Of course, this is a, first of all, this is a question about the function, no more about the equation. And second, of course, it is connected to the sign of the quadratic function, of course. So we have to look to the sign of the quadratic function in order to see when this can happen. Who can tell us? What conditions should we put here to have this property?
Okay, so if the coefficient of the maximum term is positive, then we will have to have the delta less than 0 to have only positive solutions.
So first of all, to have what?
To have positive solutions. Plus everywhere, the sign of coefficient.
Attention, we don't need, it depends what you mean by the word solutions. Solutions of who?
Oh, okay, no solution. To the function to be greater than 0 every time.
Exactly. So if we look to the sign of the quadratic function, we see that this is possible. Look, if we can imagine how the table of sign looks like. This request here, written here, means that we would like to have the following table of sign, this one, yes. And you said very correctly that this happens, first of all, when delta is negative. I mean, only in the first case, when delta is negative, is it possible to have the same sign from minus infinity to infinity. And what sign? The theory says we have the sign of A, so A must be positive. So this is how I would write the condition. First of all, delta must be negative to have the same sign from minus infinite to plus infinite, and then A must be positive. So if we put these conditions, now everything will be obtained. Attention, this inequality was already solved when we made here the table of sign of delta, yes, remember. Now we take when m delta is negative. And A positive, of course, A it's m. M must be positive. It's clear what we finally get here. It will be m belongs to minus 4 plus 2 square root of 7 over 3 infinite. This is the solution finally. Okay, but what's important is that we discovered, following the theory, the conditions. Okay, so okay, this is the affine function and the quadratic function. The simplest but very important functions in mathematics. We didn't discuss yet about the graph of the quadratic function, which is a parabola. I shall not enter into details very shortly, and then we take a break in 1 minute. The graph of the quadratic, it's a parabola. It's a curve called parabola. And this parabola looks like this or like that, depending if A is positive or A is negative. You see, on the parabola, there is a point called the vertex. Here is not exactly what I wanted to. It is symmetric, yes. It's symmetric with respect to a vertical line which passes through this vertex. The vertex is the most important point on the parabola, has the coordinates, let's call them xv and yv. The x coordinate is minus b over 2a. And yv, it's of course f of xv, which if we compute it, we obtain something like that, minus delta over 4a, but you can compute into two ways. So always when we must make the graph of a quadratic function, we always start with a vertex. And then we look to a. If a is positive, it will be like this. If a is negative, it will be like that. Okay, that's all for the moment. Now we take a break and we continue after the break.